In this chapter, we continue learning about the Earth's materials, the igneous rocks, solid from melts. Before we jump into the details about the igneous rocks, let's review what are the differences between the three major types of rocks. The source material for igneous rocks is a superhot molten rock called magma. Igneous rocks are formed by cooling of the magma. When the magma cools, series of minerals crystallized out of the melt. As temperature continuously decreases, different suites of mineral will crystallize out of the magma. And this is how we have igneous rock made. The source materials of sedimentary rocks are pieces of pre-existing rocks and dissolved solution from weathering pre-existing rocks. Why is it pre-existing rocks? Because the rocks have become pieces and solutions through weathering before they become source materials for sedimentary rocks, which is also called sediments. Sediments become sedimentary rocks through deposition, depositing in a basin and lithification, burying and compacting sediments together. The source materials for metamorphic rocks are existing rocks. Metamorphic rocks are formed when existing rocks are exposed to high temperature and high pressure conditions, but the conditions are not extreme enough to melt the rocks. The crystals in the rocks transform and recrystallize and becomes new minerals. And the structures of the rock could also change and develop folds and shared layers within the rock due to the high temperature and high pressure. Igneous rocks are formed from cooling of magma. Magma cools when it moves from the mantle toward the surface of the earth, and temperature decreases along the way. If magma eventually flowed to the surface of the earth through a volcano or a rift system or a mid-ocean ridge, the type of igneous rocks formed when magma is exposed to the surface of the earth is called extrusive rocks. When magma came to the surface of the earth, it is called lava. The extrusive rocks are formed on the Earth's surface from cooling and crystallizing the lava. If magma did not find its path to the surface of the Earth and remained underground and cooled slowly, the type of igneous rocks formed in this process is called intrusive rocks. Now we know that igneous rocks can be classified into two categories, the extrusive rocks and the intrusive rocks, based on their formation processes. But in reality, we don't have a chance to see how the rocks are formed. Then how do igneous rocks differ from one another? How do we describe the igneous rocks? To describe an igneous rock, we need to focus on two aspects, texture and composition. Let's talk about texture first. Texture is the physical property that describes the size of a crystal in the rock. The common term to describe texture would be fine-grained, coarse-grained, and mixed. The fine-grained and the coarse-grained terms are too simple. There are some more technical words we use to describe rocks. They are including pegmatic describes the rocks as very large crystals, greater than 2 to 3 centimeters in diameter. Pheneritic texture describes the rock has crystals large enough to be seen by naked eye, but smaller than the pegmatic texture. Aphanetic describes the rock that does not have large crystals. It is fine-grained crystals, and you cannot see the individual crystals from your naked eye. Porphyritic Porphyritic describes the rock that has two distinct sizes of crystals. So we have one group of relatively large crystals and a group of crystals small in the background, or we call the ground mass. Glassy. Glassy describes the igneous rock has no crystal. It is pure glass. And on the surface of the glass, if the glass is fractured and the surface will be curved, it is called conchoidal fractures. Pyroclastic describes the deposition of volcanic materials when a volcanic explosion happens. So it is a volcanic ash and fragments that are piled and compacted. Vascular describes a bubbly texture that the rock has pores inside. The formation of textures in igneous rocks are related to the cooling rate of the magma. Magma is molten rocks. Crystals in igneous rocks can only form when temperature decreases and reach the mineral's crystallizing temperature. Different minerals have different crystallization temperatures, and different minerals will form as the magma continuously cools. Therefore, how big the crystal can grow is depending on how fast the cooling process is. If the magma cools fast, the crystal do not have enough time to grow big, while if magma cools slowly, the big crystal will have enough time continuously crystallize and grow bigger and bigger. Therefore, the texture of igneous rocks are reflecting the formation process of the rock. Based on the process, we know that extrusive rocks are formed when magma cools and the minerals crystallize at the surface of the earth from lava. The cooling rate is very fast. Therefore, extrusive rocks are characterized by textures like aphanitic, vascular, porphyritic, glassy, and pyroclastic. Intrusive rocks are formed when magma remained beneath underground. The cooling rate is slow. Therefore, intrusive rocks are characterized by textures like pegmatic and phaneritic. Basalt is a typical intrusive rock formed from cooling of magma. Lava flows on the ground and gradually cools and forms basalt. Sometimes we can see flowing structures from the body of the basalt. It does not have visible mineral crystals. The texture of this outcrop in the picture is aphanitic and vascular. Obsidian is not composed of minerals. It is glass. The texture is glassy, and you can see that the conchoidal fractures on the surface. Pumice is a typical volcanic rock. When a piece of pumice was thrown out of a volcano, it was not fully crystallized. Crystallization continued as the rock transported through the air and formed vascular texture. So you can see textures help to reveal the formation process of rocks. The intrusive rocks all have larger size crystals than the extrusive rocks. From these pictures, we can recognize two groups of minerals in all of the three rocks. They are light-colored minerals and dark-colored minerals. The most recognizable difference among the three rocks is the relative amount of the two groups of minerals. From gabbro, diorite to granite, the amount of dark-colored mineral is decreased. This is due to the compositional difference among the rocks. Gabbro is a mafic rock, diorite is an intermediate rock, and granite is a felsic rock. Mafic, intermediate, and felsic rocks are all characterized by different mineral assemblages. For you easy to remember, mafic rocks contain more dark minerals, and felsic rocks contain more light-colored mineral. And the intermediate rock is the transition type of rocks between them. The dark-colored minerals are abundant in mafic rocks, are mostly olivine, pyroxene, amphibole, and biotite. They are silicate minerals contain relatively high amount of iron and magnesium, while the light-colored minerals abundant in felsic rocks are usually lack of iron and magnesium, and the light-colored silicate minerals are quartz, feldspars, and muscovite. Here are the names of common igneous rocks. Mafic intrusive rocks is gabbro. Mafic extrusive rock is basalt. Intermediate intrusive rock is diorite. Intermediate extrusive rocks. Now let's see why mafic and felsic rocks compositions are different. Magma are molten rocks, originally from deep part of the lithosphere, where temperature is high and much higher than 1000 degrees Celsius. As I said earlier, as magma cools, a series of minerals will crystallize from a uniform parent magma. The Bowen's reaction series explains how and why minerals crystallized out of magma in a sequence. Here's a video to explain the Bowen's reaction series.
Let's start with a theoretical magma. In the magma is the basic bulk chemistry found in the mantle. These individual anions and cations are the magma constituents, the stuff that makes up the magma. Now, as this magma begins to cool, mineral A begins to crystallize. Mineral A is made up of these anions and cations. As those crystals form, they take magma constituents out of the liquid. When they do, the overall bulk chemistry of the magma changes. Eventually, mineral A changes the bulk chemistry so much we cannot make any more mineral A. Then mineral B begins to crystallize, and while doing this, it's taking away additional constituents out of the melt. Then mineral C begins to crystallize, and so on and so forth. This is an oversimplification of Bowen's reaction series, which, by the way, is an oversimplification of what actually happens. Okay, peeps, we better spend a few minutes talking about Bowen's reaction series because, in my opinion, this diagram is probably one of the most important diagrams in introductory geology. It's at least in the top 5. But before we talk about what's happening here, because there's a lot going on, let's just talk about the scales on either side. So if you look on the left-hand side, you see a scale for temperature. And at the top, it's about 1300 degrees Celsius, and at the bottom, it's about 750 degrees Celsius. On the far right, you see a scale for what is essentially bulk mineral composition. Remember that mafic means that a mineral or rock is rich in magnesium or iron, while felsic means that a rock or mineral is rich in silica. Okay, so now you see we have a discontinuous branch and a continuous branch. Let's talk about the discontinuous branch first. If we have a magma that's 1300 degrees Celsius and we start to cool it down, the first mineral to crystallize is olivine. And, olivine continues to crystallize for a while until we reach a certain temperature, at which point pyroxene begins to crystallize. And you can see there is a little gap there where pyroxene and olivine are both crystallizing at the same time, but eventually, as the magma continues to cool, olivine no longer crystallizes. Now, it's important to keep in mind that as a mineral is crystallizing, it is taking element constituents out of the magma. So the magma continues to cool and pyroxene is crystallizing, and then we get to a point where amphibole begins to crystallize. And for a time, pyroxene and amphibole are crystallizing, and then we get to a point where no more pyroxene crystallizes, and now we only have amphibole crystallizing. And as we continue to cool down, we get to a point where biotite begins crystallizing. And then biotite is crystallizing for a while, and then we have no more amphibole. On the continuous branch side, we have something a little bit different going on. We only have one mineral crystallizing. That's plagioclase, which is a feldspar. The thing is, plagioclase can either use calcium or sodium as its cation. So if a magma is really warm, as it starts to cool, you will crystallize the calcium-rich plagioclase, and as the magma cools, you will begin to crystallize the sodium-rich plagioclase. But keep in mind, the plagioclase can actually have a mix of sodium and calcium. Sodium and calcium in plagioclase are substitutes for one another. Okay, so then we get to the point at the bottom third of this diagram where there's only one path now. It doesn't matter if you were on the continuous branch or the discontinuous branch. And I guess I should mention that the continuous branch and the discontinuous branch are crystallizing at the same time. So then we arrive at the bottom third of this diagram, and we only have 3 minerals left to crystallize: potassium feldspar, muscovite, and quartz. Quartz, of course, being composed of entirely silica. So we begin crystallizing ultramafic minerals, then we move to more mafic minerals, and eventually we crystal out felsic minerals. Something important that I should point out is that this diagram can run in the other direction. Let's say we built a rock somehow that had olivine and pyroxene and amphibole and biotite and plagioclase and potassium feldspar and muscovite and quartz. Those kind of rocks don't really exist in real life, but let's just say we made one and we started to melt it. Well, the first mineral that would melt would be quartz, and then the next mineral to melt would be muscovite, and then the next one would be potassium feldspar, and then we'd start melting biotite and the sodium plagioclase. Let's say I take a piece of the mantle and I don't melt it all the way to 1300 degrees C. I only melt it to maybe 900 degrees C. In that case, I might only be able to crystallize out of that melt biotite, maybe some sodium plagioclase, and then the potassium feldspar, the muscovite, and the quartz. What this diagram really illustrates is how we can get such a diversity of mineral assemblages by just melting a single piece of the Earth's mantle.
To the last, we know that the extrusive rocks are formed at the surface of the ground, and they present themselves as lava basalt, volcanic ash, and pyroclastic rocks. While intrusive rocks are formed underneath the ground, the body of intrusive rocks are called intrusions. The different types of intrusions include batholiths. They are the largest pluton, irregular masses of coarse-grained igneous rocks that covers at least 100 kilometer square areas. There's also stalks. It is also irregular masses of coarse-grained igneous rocks, but they are smaller than batholiths. Silts. A silt is a sheet-like body formed by injections of magma between parallel layers of pre-existing bedded rock. Dikes are also sheet-like intrusive bodies, but dikes cut across layers of beddings in the country rock. Okay, so that is all about igneous rocks. We learned the textures and the compositions of igneous rocks, and how texture and composition related to their formation processes. In the lab, you will have a chance to practice identifying igneous rocks. That is all for today. I hope you enjoyed the lecture, and see you next time.